This is Radio Eco Shock with Alex Smith.
We had terrible wildfires in so many places in recent years. California, the whole West, Australia, Canada, Siberia. So it is a shock when new science finds Earth was a smoky place even before the Industrial Revolution. And that could mean our planet may not warm to the very worst extremes shown in the latest climate models, or in some of them. We're fortunate to have reached a senior scientist at Harvard with expertise on wildfire smoke and climate change. Dr. Loretta J. Mickley is Senior Research Fellow at the School of Engineering and Applied Sciences. Loretta is senior author in the new paper, and the title is Improved Estimates of Pre-Industrial Biomass Burning Reduce the Magnitude of Aerosol Climate Forcing in the Southern Hemisphere. Of course, we will talk about what all that means. It was published May 28, 2021 in the journal Science Advances. The lead author is a recent grad student, Pengfei Liu. Loretta Mickley, welcome to Radio Eco Shock.
Thank you for having me, Alex.
It is a record hot spring here in the West with developing drought. I smelled a little wildfire smoke outside my door last night. Wildfires have broken out in the U.S. and Canada early, smoke going as far as New England. The assumption has been that climate change is driving more fires compared to a tranquil time before humans started burning fossil fuels. Loretta, why did your team question that?
Okay, so let's begin with the Western U.S., first of all. And then I'll switch to the Southern Hemisphere, which was the focus of our recent paper. So in the Western U.S., there has often been very intense fires in the past. We can tell from charcoal records in the soil that during warm periods in the past, fire has really spread across much of the Western U.S. In recent decades, two things have happened. First of all, over the 20th century, there's been a suppression of fire. There was a real effort to allow people to move into lots of places in the West and to keep the West relatively fire-free. And that has allowed, I say relatively fire-free, that has allowed an accumulation of very dense vegetation to grow, leading to what is sometimes called a fire deficit. But along with this accumulation of fuel, the weather has become warmer and drier as a result, we think, of climate change. And that's another pressure on fires in the Western U.S. We know that fires need dry, abundant fuel to burn and to spread, regardless of who sets the fire, whether it's lightning or a human being accidentally starting a fire. What spreads the fire is this warm, dry weather that allows lots of dry, abundant fuel to feed the fire. So the recent increase in fire in the Western U.S. is due to a combination of factors, the accumulated fuel, but also especially climate change. And we think that the fires will continue to increase in future decades as the climate continues to warm. Now, going to the Southern Hemisphere, a big question was just how much fire activity there was in the past. And that's an important question because we want to understand how the climate has evolved over many centuries. Should I pause here and ask if you have any questions right now?
No, I think you're doing well. My only question would be, why would you choose the Southern Hemisphere, which has less land mass and fewer people living there, and rather than the Northern Hemisphere?
For one thing, we had a really nice array of black carbon measurements in ice cores. What is black carbon? It's sometimes called soot. And we worked with a really magnificent ice core chemist named Joe McConnell, based in Nevada, who takes these long ice cores drilled out of the ice in Antarctica and this also in Greenland, and he looks at how black carbon or soot has varied over the decades going back in time. And for this particular project, we wanted to look at the southern hemisphere because it's a much simpler hemisphere. There are fewer influences, less human activity, more of the natural world, we thought, going back in time. So we had this really nice set of ice core records that both Joe and others had captured over the centuries. And I want to show, forgive me, I want to show a plot of all of the ice core measurements that we used for this study, going from 1750 to the year 2000. And you can see there's a lot in gray, the interannual variability at each site. So here are all 14 sites that we looked at, and here's the time series of black carbon. The black shows a kind of running mean over a number of years for each of these sites. And you can see that many of the sites show lots of interannual variability, but generally it's fairly flat until you come to the late 20th century. So here we go, fairly flat, bumps and so forth, and then you get this big increase. Some of them actually show decreases from the 1850s into the present day. So we were curious about that. So we were wondering what's causing all this black carbon, all this soot back in the 1700s. And I'm going to stop sharing the screen right now. Forgive me. Sorry. Okay, so we wondered what's the source of the black carbon or soot going back in time. And soot occurs whenever you have some kind of combustion, either from home heating, or it could be wood burning, dung burning, or power plants, industry, diesel fuel. All of that leads to BC, or black carbon or soot. And in the past and in the present, we have fires. So we know, given that there are relatively few people in the southern hemisphere in the 1700s, we figured most of that black carbon or soot was coming from fires. We didn't know what kind of fires, but we thought this must be a record of fire activity. And so we worked next with a chemistry model to try to capture this progression of black carbon or soot over time. So at Harvard, we've developed a very beautiful, in my view, model. It's been the work of many hundreds of scientists called GeoSChem, and it captures the chemical composition of air, all the particles, all the trace gases, and it works a little bit like a weather model, only instead of having just weather moving around the Earth, we can actually capture the movement of smoke plumes, for example, or the transport of plumes from power plants. We can begin to see how the pollution spreads around the globe. And I really want to credit, these hundreds of other scientists who have contributed to GeoSChem, including the lead scientist, Daniel Jacob, my colleague here at Harvard. In any event, we tried to implement the standard emissions from fires, smoke emissions from fires, into GeoSChem. And we were not able to capture the trend of soot or black carbon from the pre-industrial era, 1750s, to the present day. And I'll try again to share my screen, see if I can get that picture up. Share. And Yeah. So this picture here shows from 1750 to 2000. The ice core measurements are in black. This is the average over all 14 ice cores in Antarctica. And the gray shows the variation amongst these sites. And we tried first putting a very standard scenario of soot emissions into our model from 1750 to 2000. This is a scenario developed by the Intergovernmental Panel on Climate Change. It will be used in the coming assessment report, the sixth assessment report on climate. And we found that our model did not capture any of this trend going back in time. There's lots of variability in the observed trend, but look, there's this big model measurement discrepancy. We weren't sure why. Now, you may ask, first of all, where is this biomass burning occurring, or where are these fires occurring? We know from other model experiments that these emissions are occurring in the southern hemisphere. Northern hemisphere is just too far away, and the soot, the smoke will get rained out or get deposited to the Earth's surface long before it gets to the Antarctica. And we did some more studies, and we determined that much of the soot that reaches Antarctica is coming from the southern hemisphere, the southern part of South America and Africa, and then Australia and New Zealand, present-day Australia and New Zealand. So that's where this black carbon is coming from. There's no industry. There are no power plants back in the 1750s. All of this must be coming from fires, and yet we can't capture it with the standard emissions from IPCC, Intergovernmental Panel on Climate Change. So then we turned to a collaborator of ours named Jed Kaplan. Jed Kaplan has developed a really wonderful land cover model, a vegetation model, that takes into account the whole carbon cycle of growth and destruction and fires. And his model also takes into account the fire practices of indigenous people. We know that during this time period, there were many indigenous societies living in the southern hemisphere. And Jed has worked with anthropologists to understand the fire practices of these peoples. And indeed, there is much burning in their traditions. They use burning to clear the land for their agriculture. They use burning to clear the land to facilitate hunting. And when we implement Jed's smoke emissions, into our model, we get a different picture. And I'm going to skip ahead a couple slides to a new slide that shows some of the same material from the last picture, with the blue being from the standard called CMIP6 or IPCC fire emissions. The black is what we observed in our ice cores. And now the orange is our new model results. These are ratios, actually, from the pre-industrial to the present day of black carbon. And we can see that, in fact, we get a better match with the present day going into the past with these okay, so our simulations using the new model that Jed Kaplan developed called LPJ Fire, we're better able to capture the evolution of fire going back in time compared to the standard IPCC CMIP6 emissions. We get 4 times more black carbon, 4 times more soot. So our simulations using the new model, LPJ-LM-FIRE, better captures the observed evolution of smoke in the past, going from 1750 to the present day. So the black is what's observed. The orange is our new model results doing snapshots at different time intervals. And the blue is what we get from IPCC, which is way underestimating what is going on.
But here is a strange thing, I think, for many of our listeners. In 2017, a team led by Neil Andela at Cardiff University published their paper, A Human-Driven Decline in Global Burned Area. It seems like farmers are burning less of their fields in the savannas and so on. And yet you're showing black carbon remains more or less the same or rising while forest area burned is going down. How does that work?
Yes. Okay. So what we think is happening is that in the recent decades, the paper you're talking about, the Andela paper, looks at just these decades here. And what we think is happening is that in the 20th century, as fire declined, the black carbon from industrial sources increased. So I should say this orange curve includes both fires and the industrial sources. There wasn't enough room to have all this text in here. So this includes the revised model results from the fire model as well as emissions from industrial and urban sources.
So fossil fuel emissions are picking up the slack of what might have been decreased soot from burning fires or wildfires.
Absolutely. So as the fire emissions decrease, there's an increase in the emissions from industry and power plants. And I want to say that the Andela paper that you referred to is really a wonderful paper. And what they see is a decrease in fire due in part due to passive suppression. What is passive suppression? That's the building of roads that can serve as fire breaks. And that's also the result of agriculture making clearing out the fire-prone vegetation. So we call that passive suppression. And indeed, that has led to a recent decrease in fire activity.
Well, here in the village I've lived in, smoke so thick you couldn't see across the street. And it was cold and it was dark, even though otherwise it would have been very, very hot during that time. It was a heat wave, but it was cold. So what I think many of the public are confused about is the smoke from wildfires a cooling factor or is it a heating factor regionally and then for the whole global climate?
That's such a good question. And this is the second part of what I'd like to talk about today, is what are the effects of smoke on climate? How does smoke perturb climate? And smoke consists of an array of tiny particles, different kinds of particles, and gases. We focus mainly on the particles because we think they have the larger climate effect. I should also note fires release CO2. But that CO2, if it's a healthy biosphere, will be taken up again as the vegetation returns after a fire. So that's kind of CO2 neutral. A good fire, a healthy planet will release CO2 with fires and then draw it down again as the vegetation returns. So in addition to CO2, you have short-lived gases like ozone and other formaldehyde, other gases coming from fires. And then we have particles. We have very dark particles called soot or black carbon. And then we have lighter colored particles called organic carbon. And they have multiple roles in perturbing climate. When they're in the atmosphere, black carbon absorbs sunlight. Organic carbon reflects sunlight. Both of those processes, either absorbing sunlight or reflecting sunlight, lead to less sunlight reaching the Earth's surface. And that may account for some of the cooling that you've experienced out west when there's a fire nearby. So you get local cooling. The black carbon may actually warm the upper layers of the atmosphere because it's absorbing. So these effects, this first category of effects, is often called aerosol radiation interactions. And they kind of balance out because the black carbon absorbs and the organic carbon reflects. So overall, the temperature response tends to be neutral, although you may get cooling at the surface locally. But there's another very key impact that these particles have on climate, and this involves clouds. So as you know from your previous guest, Jessica Turney, clouds require water vapor, but they also require little particles that act as seeds for the water vapor to condense on. And if you don't have any particles, it's hard to get a cloud beginning to show up. So you get these little particles in the air, the water vapor condenses onto the clouds, and under the right conditions, the right temperatures, and right humidity, these cloud droplets can grow and grow and grow, and you get a cloud, a stratus cloud low or a cumulus cloud that blows up. You get these clouds forming. And the more particles you have, the more cloud droplets you have. And the brighter the clouds are. And these clouds, especially low clouds, can reflect sunlight. And so downwind of the fires, as the smoke evolves, you can get clouds forming because they're providing little particles for the cloud droplets to condense on. This is way downwind of your village. So are you okay so far?
Oh, definitely. Keep going.
Okay. So as you learned from your previous guests, knowing cloud cover in the past has been very, very hard. Clouds don't leave a record. There's no proxy that I know of for clouds. There's no fossil record of clouds. They erase. So how do we know clouds in the past? Well, in our work, we tracked the smoke going from South America, Africa, and Australia, New Zealand. We tracked that smoke and determined what does that do to the cloud cover in the southern hemisphere? And then how will that cloud cover affect the whole hemispheric temperatures, not just locally, but the whole hemisphere. And we found that the particles produced by this more fiery past in the southern hemisphere led to an abundance of clouds, of little abundant cloud droplets that reflected the light. And so we have, in effect, an abundance of particles in the past that we didn't previously appreciate. An abundance of particles, an abundance of cloud droplets that led to greater cooling. We might have had a greater cooling effect than we thought. Now, going forward, I think we know the temperatures pretty well in the past, but we had a greater cooling effect from the clouds. Going forward, most models say, oh, not much cooling from particles until we get to the present. And all of a sudden, we have the big industrial revolution, and all the particles ramped up. So we have this huge cooling effect. This is a standard view. We have this huge cooling effect in the present day. At the same time, we have this huge greenhouse gas warming in the present day. And in order to account for, to explain the rise in temperatures from the pre-industrial to the present day, modelers have had to say, oh, well, the greenhouse gases must be very powerful. We need that big push to overcome that huge cooling from all the particles. Okay, follow me so far?
Yep.
Okay, however, we say we've had that cooling all along. It's been fairly constant. So when the greenhouse gases come in, we don't need a big push from them to account for the cooling to account for the warming due to greenhouse gases. We don't need such a sensitive atmosphere to the increase in greenhouse gases. Now, is this good news? Well, I'll come to that in a minute, but let me ask if you have any questions.
Well, I just wanted, before we run out of time, to insert the idea that this stuff is deadly as well. In February this year, you also co-authored a paper titled Global Mortality from Outdoor Fine Particle Pollution Generated by Fossil Fuel Combustion, came up with a figure of around 10 million deaths a year, which I would say is 3 times the official death toll for COVID so far, and yet we don't seem to be doing anything about it. What would you say about these fossil fuel particles that are killing millions of people?
These are indeed estimates, and I should say in 2018 we amended that to be 8 million, given the decrease in particles from China. These are particles from fossil fuel combustion, not from fires. So it's a different class of particles. So why aren't we doing more about that? I think there's a lack of awareness of the impact of fossil fuel combustion on human health. It's a very tough problem because many countries want to have electricity. They want to have cars, including us. You know, we want to develop. We want to mine Bitcoin. We want to have a comfortable life. And so we have this huge amount of fossil fuel combustion that leads to particles in the atmosphere as well as CO2. So our hope with that paper is that people will recognize that in addition to the dangers of greenhouse gases, there's a danger from breathing the accompanying particles that are produced by fossil fuel combustion, and that we should probably consider that as a very real and present danger of such combustion.
Okay, well, let's return to your new article. And you were hinting that maybe there's some good news in it, or maybe not. Why don't you let us know, what should we think about this? Because it's very complex here. Despite the TV news, fires may not be any worse. They could be a warming feedback. Millions of people are dying from air pollution. It's a lot to take in. So how do you summarize what your findings mean for us now?
That's a great question. So one of the big uncertainties is how will the climate change in the future? What will increasing levels of CO2 do to our daily lives? And that's a very hard thing to predict. And our work on the pre-industrial atmosphere, we hope will give a little bit more insight, help us pin down the true sensitivity of the Earth's surface temperatures to increasing greenhouse gases. That's our hope. That there's a lot of uncertainty in how the Earth's surface temperatures will respond in the future, and we hope that by providing a little bit of a window into the past, we can better constrain what will happen in the future. And I want to make clear that although our work does not suggest these very high sensitivities that some modelers see, we still face really important decisions and a bleak future if we don't rein in the emissions of greenhouse gases.
From the School of Engineering and Applied Sciences at Harvard University, we've been speaking with Senior Research Fellow Loretta J. Mickley, and you can find links to all the science we talked about in my show blog published weekly at ecoshock.org. Loretta, thank you for helping us out. I'm sorry we ran out of time. We could have talked for a long time and still learned from you.
Thank you so much.
I'm Alex Smith for Radio EcoShock.